Hello, everyone, and welcome to the DFINITY Foundation's headquarters out of Zurich, Switzerland. My name is Tracy Trachsler. I'm the head of institutional relations at the foundation, and I'm really excited to walk you through what's going to be an exciting half an hour or so as we dive into the celebration and reflection on 3 key milestones recently achieved. I am joined by the 2 people that are most qualified to walk us through each of these milestones. The first being Jan. I'll give him the opportunity to introduce himself.
Hi, I'm Jan. I'm the CTO at the DFINITY Foundation.
And we are, of course, also joined by Manu.
I'm Manu. I'm a senior director of engineering, and I lead a lot of the core protocol development at DFINITY.
All right. Thank you both for taking the time today. Now, before we dive into the specifics of the different milestones and what it is exactly that they've unlocked in terms of possibilities, I'd like to quickly zoom out and set a bit of context. So for those who may not be familiar, or for those who may appreciate a bit of a refresher, let's say, what is the overarching sort of world computer vision of ICP that guides its development? Jan.
Right, the world computer mission is like what kept us excited for the last 6 years or more. And the idea here is really like, to build the world computer or maybe the internet computer protocol, which by itself says what the whole goal is. It is a protocol that runs on the internet computer, a protocol that runs into the internet and extends the internet into like a computing platform, so that you can run software on the protocol, on the network, just very much as like today, like most people communicate over the internet, but in the future, like most people will compute over the internet.
I guess then the natural follow-up question to that statement is, why would you want that?
I guess like one very prominent example here is Bitcoin. Bitcoin is a protocol. It runs on the internet, right? It has like the Bitcoin miner who actually run the protocol and like sovereign hardware. And Bitcoin has never been hacked, right? So that's why it's very secure. It's actually the reason you want to run software on a protocol, because it's secure, it's sovereign, it's unstoppable. And the mission of the DFINITY Foundation is really to extend this paradigm to like all of software, because like Bitcoin is a very limited compute functionality. How many Bitcoin belong to whom, right? The Internet Computer Protocol already does allow you to do very complex, very compute-intensive computation. I guess today's milestone actually show that we have extended that even more, and we won't stop here.
All right, so we'll dive into each of the milestones in a second. But Manu, I would be curious. So with this world computer vision in mind, how did that sort of greater overarching goal inform some of the specific choices made with regards to the internet computer's architecture?
As you can tell from Jan's statement, this is a very ambitious vision, right? We want to run more and more software as a smart contract on the blockchain. And that comes with a lot of requirements. So for one, it cannot be super expensive to run software this way, then nobody would use it. And so to keep costs low, we minimize replication while trying to still get great decentralization by having typically subnets of 13 nodes, 13 to 40 is the subnets we have now, that are as different as possible, different countries, different data centers. And so by having lower replication, the cost can be lower. We also need it to be scalable, because we want more and more of the world's software to run on this platform. And so for that reason, we have the subnet architecture, where more subnets can always be added, which then grows the total capacity of the internet computer, and subnets can seamlessly talk to each other. We also want it to be very easy to use, because if I run my software there, I don't want my users to suffer because it's such a painful system to use. And so that's why you can interact with the internet computer from your browser. It uses a reverse gas model, to basically take all hurdles away. And finally, we have like an execution model that is based on WebAssembly or WASM, which allows for different programming languages to use, which lets developers make a choice and build advanced applications.
A lot of people also know like Bitcoin is very slow and costly, and the internet computer protocol is entirely different, right? It is fast. It is as fast as like a single computer essentially can transact software. And also cost-wise, right? Even the traditional cloud stack, they have a lot of replication, content distribution, and so on and so forth. And if you look at it, like what we have now with the computer is actually less replicated than the traditional IT stack is. And so at the end of the day, like running software on the computer protocol will be cheaper than traditional cloud hosting.
All right, so let's take a look at sort of the overarching goal, I guess, of the roadmap itself before we touch on the individual milestones. How does the roadmap actually factor into the development efforts of the foundation team? Manu.
I think it helps focus, essentially. I mean, we have this ambitious vision. There's many things you can always improve, right? We have all sorts of ideas. And I think thinking very hard and discussing with everybody what are the most valuable things we can do, and then capturing that in the roadmap and then executing on that, just a good way to basically structure your thoughts and then focus and achieve some things and then move on to the next thing.
So is it fair to call it sort of a blueprint for priorities, let's say?
Exactly, yes.
It also helps to communicate, right? What we're working on. It helps to collect feedback from the customers, the users of the Internet Computer Protocol, the developers. You know what's coming up. On the one hand, they can plan, but then also they learn, okay, so now their pain points are going to be addressed next, or maybe a little later, and then they can talk to us and say, there's really no way you should do this first and this. It's both, right? It's a means to communicate with the rest of the world what the foundation is up to. And as Manu said, it's also like for the team to know, okay, now let's head towards this thing, this roadmap, and also celebrate them as we do today, right? It's an achievement. Everyone is an achievement. Every one of the roadmaps, every one of the milestones is an achievement, and we should also celebrate once in a while.
All right, so before we dive into the specific technical details of each individual milestone, I'd like to take a look at the milestones as sort of a collective improvement and reflect on what exactly it is that these three particular milestones actually enable. And I think we've sort of summarized it as speed, storage, and simplicity. So I'd like to take a look at what we mean by each of those terms in turn, starting with speed. Can you tell us a bit, Manu, with regards to the overall improvements on the speed side?
Absolutely. So with speed, I think we mainly mean latency, so end-to-end latency for the user. And we essentially cut the latency in half. So we made a big improvement there. And concretely, that means that now if the user clicks a button which triggers some message to the internet computer, then all the processing until the user gets a trustworthy response back takes on average 1.3 seconds. And so that used to be more like 2.5 seconds. And I think this is a meaningful improvement where it feels much nicer as a user. You don't notice much of a delay. You're not really waiting. So I think for user experience, this is a big improvement.
So I guess for an end user, this feels almost instantaneous. Is that fair to say?
I think so.
All right, so big improvement from a user experience side of things. Let's take a look at the second component, which is storage. What improvements were made on the storage side?
Yeah, there's a number of metrics that we increased there. So each individual canister smart contract can now hold more data, it can hold more memory. This is increased to 500 gigabytes. So you can do a lot of things with 500 gigabytes.
As a frame of reference, how does the 500 gigabytes match up to where we started?
Yeah, so at Genesis, it was 4 gigabytes, and it was gradually increased over time. And so now in the last 3.5 years, it changed a lot, yeah.
Any other components on the storage side?
Yes, so we also made it easier to get a lot of data into your canister smart contract. So now you might want to have 500 gigs there, but if it takes forever to get it there, then you still have a problem. So we significantly increased the bandwidth of the blockchain in some sense. We made it more than 3 times as fast. So now you can upload with more than 6 megabytes per second, and we have plans to grow that even further. So it's easier to get a lot of data into your canister smart contracts. And then third, we made, this is specific to Motoko, so the programming language purpose-built for the internet computer. how we deal with data there, especially when you upgrade. And so we call this enhanced orthogonal persistence. And I think the summary is that you essentially, as a developer, don't need to worry about your data. You can just upgrade the code of your smart contract and all the data is still there. And this makes it easier to hold large amounts of data, whereas previously there was some serialization, deserialization sometimes involved, which was limited what you could do.
Jan, I'd be curious, does increasing the storage capacity of an individual subnet have any knock-on effects in terms of tokenomics?
It does, in fact, right? I mean, so the amount of storage, not a single canister, but like that you kind of have on a subnet. Of course, we want it to be as big as possible because every node right now has 40 tera of storage, but we can't really use all of that yet because the storage that is available to canister has to be replicated across all the nodes. So that means they have to synchronize all that storage, and nodes have to catch up. They have to communicate that. You have to build hash trees over that. So it's a lot of computation that is necessary over that amount of storage. And so that means right now we can use like 1 tera of that 40 tera of the nodes. And so that also means that the amount of storage that can be used and can be paid for by smart contracts is like just a fraction of the storage that is available overall. And at the end of the day, you want to recover the full cost that these nodes cost. And so obviously you want to recover, or you want to be able to use the full 40 tera. I mean, you cannot use everything. Of course, there is like overhead here and there. But of course, we're pushing much further with that. And so, right, the more you can use, the cheaper it gets, the less it costs to smart contracts, but also the overall tokenomics work out better, of course.
So a major improvement there, it's fair to say. I'll let you close out the loop in our little trifecta between speed, storage, simplicity. Simplicity. Why do we want things to be simple?
Well, we want to attract as much developers as we can. Again, world computer means like everybody should code on the inner computer. And so it has to be as simple as we can. And obviously it's a new platform, so there's like a lot of new concepts that you have to learn as a developer. And also if you develop a new platform as opposed to like a traditional platform, like a lot of tools are available, tools for debugging, tools for taking backups. And here now on the inner computer, we just introduced the snapshots, canister snapshots. So that means you can like store, like take a snapshot of your current application, right? And then upgrade it and see whether your upgrade works out. And if it doesn't work out, you roll back. And we all know how hard it is to make backups of our data, maintain that. And now on the inner computer, actually, you can do that automatically. Or the protocol supports that. Of course, as a developer, you still have to, like deal with that, I guess. Then also, like debugging your software, reading like error messages like that is also like something that was not so easy before on the internet computer protocol. In particular, since when a smart contract is executed, it traps because of some error, it just gets automatically rolled back to its original state, or when it takes too long and so forth. But that also means you have no information available, what went wrong, what happened. And now here we have like log error messages that actually persist that. And so if something went wrong, you can actually, developer go and read that log, and you can try to find out what you should change and how you can improve.
So overall, really improving the developer experience, I guess, for those that are looking to build more advanced applications or to start building applications on top of the internet computer itself.
Yeah, the milestones really had something for the users, for the developers, for the whole world at the end of the day.
Everyone benefits in the end. Obviously, when we take a look at all three of those individual items collectively, that represents a massive R&D effort. I'd be curious, Manu, if you had to put a number, let's say, on the overall time, et cetera, that has been spent on these milestones, what does that actually represent?
Yeah, I would guess like 10 person years. It was a huge R&D effort.
Well, congratulations. So let's dive into the actual R&D effort itself a bit more closely by taking a look specifically at the individual technical changes that were made as part of each milestone. Let's take a look at Tokamak. Can you sort of unpack or explain at a high level the work that was done for this particular milestone?
Yeah. So we worked on different layers to reduce this latency as far as we can. So the first thing is that we made a lot of changes to the networking code. So because it's a distributed protocol, different replicas need to communicate with each other to process my message. And this peer-to-peer logic has been rewritten to use the Quick protocol, and many improvements have been made, and overall leading to the fact that replicas can now exchange messages faster. And this in turn also lets us lets the subnet grow the blockchain faster because of this faster networking that they have. So you see that subnets can now you see that the subnet blockchains now grow at 2.5 blocks per second. And of course, this has a positive effect on user latency because my message needs to be in the blockchain before it can be processed. So this is one angle. The other is that when I send a message to the internet computer, it goes via a boundary node to the replicas of the right subnet. And this, of course, is another step that adds latency. And these boundary nodes are now aware of the latency to various replicas, and so they now choose replicas that are relatively close, so low latency, to reach the subnet, which helps. And then third, the way that the user and the system communicates has been improved, whereas previously I would send my message, and now I would repeatedly ask, hey, did you process my message yet? And this polling adds latency as well. And the way it works now is that there's a new way to send your message, which is synchronous, meaning that as soon as the message is processed, it immediately pushes back to me saying, here's the result of your message. And so overall, these three factors led to a big improvement.
Let's take a closer look at Stellarator. What exactly were the different components that went into that milestone?
Yeah, so a lot of effort went into how the replicas, the nodes that power the internet computer, store all the state, all the memory of all these canister smart contracts. And because this can be large, this is quite a complex thing. This whole storage layer has been rewritten to use log-structured merge trees, or so we call it the LSMT storage layer. And the main thing to know is that this allows us to kind of sort of spread out the work. We don't need to, at one point, write everything to disk, which is very slow, but instead we can kind of make changes and then combine them later, so we can spread out the work and efficiently deal with large states. And so this lets us have more state per canister smart contract and have us more state in total on every subnet. To increase this bandwidth to canisters, we made it smarter how we used the blockchain. How it used to work is that some machines need to send all their messages to everybody else at one point, and everybody else is kind of waiting, and then the next person is busy. And so we were not really utilizing the bandwidth very well. And what we do now is that we disseminate these ingress messages all the time, and then on the blockchain only agree on some hashes of messages that you already have. And this way we can utilize the bandwidth between the replicas much better and overall have a significantly increased throughput. And then for this Motoko enhanced orthogonal persistence, we basically use the fact that Motoko is purpose-built for the internet computer, and so we know the compiler and how the memory layout works, and so we essentially a lot of effort went into this, enabling us to upgrade canister code while keeping all the state in a compatible way.
All right, and let's close things out with Beryllium. I think Jan's already touched on quite a few components, right, from snapshots to logging, etc. But maybe if you can just quickly recap the individual components of Beryllium.
Absolutely. So we introduced the snapshotting ability. So you can take a whole snapshot of your canister with code and state, and if now something goes wrong, you can easily roll back to that previous snapshot. We introduced logging functionality so that when your canister runs into an error, the state is not committed, right? Which is a good thing. It's rolled back, but that made it hard to learn about what exactly went wrong. And so now you have a logging ability which allows you to capture these things and capture errors in particular. We also added support to get back traces so that you know exactly where in the code, what exactly happened when the error occurred, which is super helpful for debugging issues. And we made the error messages easier to understand and more actionable to developers.
All right, so to close things out, obviously, again, it's important to see the work that has been done in 2024. We look ahead into a roadmap that certainly doesn't end here. There's plenty still to do in the remaining months of this year. And of course, heading into 2025, there's a lot of key milestones that are still coming up in the next couple of months. If people are interested in checking out our roadmap in a bit more detail, seeing what's ahead and reflecting on things already achieved, where should they go?
Head over to internetcomputer.org/roadmap and you'll find like all the upcoming milestones, all the past milestones. And actually, you should, give us feedback on it. Have a look what you like, what you don't like, what you want to see more. And we're just forming the new roadmap for the next year. So if you have input, let us know and we'll take it into consideration.
And with that, thank you. And of course, more importantly, congratulations to you, to the entire R&D team. We really appreciate the blood, sweat, and tears, hopefully not too many tears, that you've poured into not just these milestones, but the roadmap in general. We're certainly excited for what's to come, many more successful milestones to be achieved in the coming months. Thank you again, and congratulations.
Nice, my God, my ear.
Oh yeah, I didn't expect it to be that loud. Huh?